All right. Um, Good afternoon to everyone. Thank you for joining us. So we are going to begin with the Knowskite-X fourth webinar that is titled New Routes, New Materials, What Remains to be Discovered. So without further ado, I'd leave the word to Elise Berrier, that is our project coordinator, and will deliver the first speech. Elise, the stage is yours.
Thank you very much, Claudio. Welcome to this fourth webinar. I will take maybe 5 minutes just to make an overall presentation of our project and to give you some examples of how important it is to cook materials and to be able to fine tune and discover new materials. So first of all, maybe not all of you know the Knowskite-X project. It's a European funded project gathering 10 partners from all over Europe. And here are our very nice faces from people from characterization, people from synthesis, including, of course, our 2 days animator, Yuri. Thank you so much for preparing this webinar. Okay, just a few words about the Knowskite-X concept. It's a science-based rational approach towards the discovering of new materials. So we are trying to combine knowledge obtained from modeling, multi-scale modeling, of course, characterization, relevant characterization, I would say, also some machine learning tools. But of course, in order to provide data and in order to characterize things, we need to prepare what we're going to characterize because we are mostly chemists. So few words on some examples of what we are doing in Knowskite-X about materials preparation. One key aspect is controlling the texture, and it's very important in both use cases we are working on, which are carbon-based materials for capacitors, electrodes, as well as perovskite and oxide-based materials for fuel cells and electrolyzers application. In all cases, it's a surface-controlled. There are surface-controlled processes, and we really need to fine-tune the texture. So this is an example that has been obtained by our partners in Athens, Greece, at the National Center for Scientific Research, Demokritos. Another example is to fine-tune the composition in order to fine-tune the functionality. And in case, for example, of the perovskites, by fine-tuning the composition, we are changing the radius of the cations that are at play in the material. And by doing so, we are inducing structural distortions. And we can also think of doping with isovalent or allyvalent species, or even think of disturbing or perturbing the stoichiometry. So this is a brilliant example obtained at INL by Yuri and Siavash on the lanthanum strontium ferrite nicolates. Because, yes, the idea is to combine a cathode and an anode. The cathode currently is made of LSCF, so thyrate cobaltate. The anode is made of nickel oxide, so why not combining all together? And by targeting these materials, it was also the occasion of showing up a new, very simple synthesis method. So I will not take too much of your time. I'm very sorry. Maybe I'm already too long, but these are 2 examples of how important is preparation activities in our project and how important it is to really look and listen carefully at our 2-day speakers' presentation from inside and outside our project. Thank you very much, and I hope you will enjoy our webinar. Thank you so much. And now the floor is yours to start the discussion and the speaker's presentation.
Thank you very much, Elise. So we can proceed with our next speaker for today, Dr. Mohammed Subrati. So when you're ready, Mohammed, you can share your screen. Don't forget you're also muted, so unmute yourself. Okay. We cannot hear you, Mohammed.
Do you hear me now? I think now it's okay.
Okay, now we can hear you. You have to share again your screen.
Okay. For some reason, I cannot share it now.
Let me see. All right, now you should.
Now I can speak, but I cannot share for some reason.
I don't know why you are really.
Okay.
You have.
Well,
let me check. Let me check. Just a moment. Okay, now you should be able to.
Yes.
Okay.
Sound screen. Do you see my screen?
Yes.
Okay, perfect.
All right.
Okay, perfect.
Thank you very much.
So, thank you, Elise. Thank you, Claudio. Good afternoon, everyone. So,
sorry, Mohammed, if you want, you can also turn on your webcam. Sorry, just this.
Add the webcam. Where's the webcam?
Well, it's the same.
Yes.
Don't worry.
Okay, perfect.
Okay, it's perfect. Now we see you. Thank you.
Okay.
Go back. Yes.
Yeah. So thank you, Elise. Thank you, Claudio. Good afternoon, everyone. So the title of my presentation today will be the recent, as you saw in the post and in the announcement, highlighting the recent advances and challenges in the utilization of carbon materials in electrochemical applications, with because it's a very broad topic. So the aim of this presentation is to cover the material aspects of this research theme, and also because there are plenty of carbon materials in this field. So I'll be just covering on the most notable ones, the graphene, and of course, which is non-porous, and the hierarchical porous carbon, which is actually the most exotic of them all, and very interesting, actually. So first, the outline of the presentation actually will be as follows. First of all, I'll be explaining why carbon, why we are doing this actually in the first place, what's so special about this family of carbon materials. And in the second part of the presentation, I'll be highlighting the differences between graphene and the hierarchical porous carbons, their synthesis, their properties, and also as I said, the recent advances, the prospects, and the challenges facing them in the electrochemical energy applications, more specifically energy storage and fuel cells. And finally, the remarks will be basically the experimental highlights of our work at Democritus within the framework of the Knowskite project, as Elise said earlier. So why carbon? What's so special about carbon? Well, perhaps the most interesting for any normal person to be facts. Actually, the first one is that carbon just barely makes up 0.025% of Earth's crust. So almost nothing, but yet you see it all around you, since it forms more compounds than all the other elements in front of you combined, as you can see in the periodic table. So why is that? Well, the answer actually is right in front of you, is because it's naturally blessed, as I like to say, with its unique location in the periodic table. To be more specific, the second period and group 14 or group 4A, which gives it, as most of you know, its electronic configuration 2s2 and 2p2. But this is in the ground state for a single carbon atom that is theoretically existing in an infinite vacuum not surrounded by any other atom. So what happens if, but this electronic configuration, for example, does not explain why methane exists, because one carbon atom that is attached to 4 hydrogen atoms. So based upon this electronic configuration, it will only bond with 2 hydrogen atoms. So the answer is that carbon atoms, when they approach or they're in the vicinity of other carbon atoms or any other atoms, they tend to promote themselves, or the other atoms, they promote actually the electronic excite, let's say electronic configuration, so that the 2s orbital and the 2p orbitals, they align energetically, let's say, at the same energy level. So, and based upon Hans' selection rule, all the 4 orbitals now can be filled equally. So now you can, in the case of methane, you can have CH4, so contribute 4 covalent bonds, so 4 sigma bonds. And what happens if instead of 4 hydrogen atoms, you have 4 carbon atoms? Then you have 4 sigma carbon-carbon bonds, which is the case in diamond, the first simplest carbon material that first comes to mind, and which everyone knows in terms of jewelry, and it's a dazzling star among carbon materials. So it is sp3, as I said, and it is thermally conductive, but it is electrically insulating. But perhaps what's most interesting about diamond is that until now, it is the hardest known material to man, 70 to 150 gigapascal on Vickers hardness scale, which makes it actually suitable construction material for the exploration diamond encrusted drill bits, which are, of course, in the first choice that comes to mind in the in geosciences and also in the oil industry to drill the reservoirs to create the oil wells. So this was for the sp3. What about if instead of 4 carbons, the carbon atom now is attached to 3 carbon atoms? In this case, you have the sp2 hybridization, and the pz orbital now can form the p bonds. And of course, in the energetically favorable hexagonal lattice, which can extend laterally infinitely, it's 2 microns, you create the the family of the 0-dimensional, 1-dimensional, 2-dimensional, of course, the 3-dimensional carbon materials that are mostly sp2 hybridized in their pristine forms, of course. But all these materials are non-porous, and of course they're sp3-derived porous derivatives, or also known as the non-graphitizing carbons, all of which are actually microporous. And the most interesting of them all, also, it is based on the graphene or graphitic sp2 hexagonal lattice, is also the hierarchical porous carbons, which actually a very unique family of porous carbon porous materials, which have actually the 3 hierarchical levels of porosity, namely micropores less than 10 nanometers, mesopores, macropores above 50 nanometers, and mesopores in between 2 and 50 nanometers. So for the sake of, since we don't have much time, so I'll be focusing actually, as I said earlier, on the simplest of this family of sp2 carbons, that is graphene, and of course the hierarchical porous carbons, which are the most interesting among the family of porous carbon materials. So since we'll be talking about electrochemical applications, so it is worth looking into the electronic properties of these materials. So we'll start from the very basic, as I said, their framework, the sp2 framework. So in this case, the pristine single layer graphene. So as you can see that on your right hand, you have the electron density of in pristine single-layer graphene. As you can see, you have a very long range p conjugation, which is actually similar to what you would observe in polyaromatic compounds. But in the case of graphene, what's so special about graphene is that compared to polyaromatic compounds, graphene extends laterally in micron scales. So very large sheets. And because of this long range p conjugation, periodic structure, let's say, we have to examine its band structure. So as you can see in at the bottom, on the top left, you have actually the unit cell in the real space of a single layer graphene, and the big, let's say the big hexagon is basically the unit cell, but in the reciprocal space, which is known as the Brillouin zone, which is highly symmetrical, and it's made of multiple non-symmetric or irreducible Brillouin zones, which are given. So basically from the center, you have the gamma point, and then you have in the center of the, let's say, of the line, that is the M or me point, and then the corner points, the 6 corner points are called the kappa or K points. So this is the irreducible Brillouin zone, and we'll see next. So we have defined a path to plot the band structure. In this case, we go from gamma, the center, to the M, to the K, and back to the gamma point. And this is the corresponding band structure. On the y-axis, you have the energy minus the Fermi level. So this means that the 0 horizontal line is the Fermi level in this case. And below the 0, you have the valence band. You know this very well. And of course, on the top, you have the conduction band. So what's unique about these graphitic materials is the shape at the K point. Keep an eye on the K point. You can see actually it's like two triangles inverted, which if you see, let's say the 3-dimensional, it looks like cones. So they are called actually Dirac cones, which are touching at the K point, literally touching. So, which means that there is no band gap, and because of this is why graphene has actually very good electrical conductivity. And if you compare, let's say, the properties of graphene with, which is sp2, with its sp3 counterpart, that is diamond, you can see actually the thermal conductivity of graphene is almost twice as much as that of diamond, which is expected because sp2 bonds are stronger than sp3 bonds. Apart from that, in diamond, because it's extending, as you saw, in 3 dimensions, so the dissipation of the phonons, the vibrations for thermal conductivity, it takes place in 3 dimensions, whereas in the single layer graphene, it takes place in 2 dimensions. So this is why it's higher, the thermal conductivity. But diamond, as you saw, it is fully occupied. All the orbitals, the sp3 or 4 sp3 hybridized orbitals. So this is why it has no electrical conductivity. It is insulating. And whereas for pristine graphene, as you saw, because it has no band gap, this is why it has this good electrical conductivity. So this was for the graphene. You can see on the first one on the left image, you have as I said, the Dirac cones. You have the P and the P, the anti-bonding p orbitals. So what happens if you oxidize graphene, which is actually graphene oxide? It's the oxidized derivative. So basically, you create sp3 hybridized domains that are carbon atoms that are bonded to the oxygen function groups. On the basal planes, you have the hydroxides and the epoxides, and on the edges, you have the carboxyls. This is the structure of graphene oxide. And because of this, you distort the sp3, the one you saw before, the sp2, the long range sp2 conjugation. Because of this, you open that gap, you widen that gap. And you can see these horizontal lines in the forbidden band in between are basically the defect state. And the Fermi level goes through the forbidden, these defect state in the forbidden band. What happens if you reduce graphene oxide? Then you restore the sp2 conjugation, but of course, nothing is perfect. You never restore, fully recover the sp2 conjugation. But as you may expect, yes, you try you close relatively you narrow the band gap. And because of they have a band gap, both graphene oxide and the reduced graphene oxide, they have band gaps. They are classified as semiconductors, actually, organic semiconductors. And this is the UV visible spectra for both. And you can see that the reduction of graphene oxide, because you close the band gap, so the excitation energy for the from the p to p star orbitals of the electronic excitation energy decreases. This is why you have this redshift. For the photoluminescence, and this is actually, you can also see it from the other way, other perspective, which is photoluminescence. In photoluminescence, actually, it's the other way around. So let's say you excite both graphene oxide, the electrons, I mean, graphene oxide and reduced graphene oxide with the same wavelength, in this case, 405 nanometers. So as I said, that in graphene oxide, as you see on the left, down at the bottom, you have in the forbidden band, if you remember, the defect state. So these red and the blue are basically the defect state in the forbidden band. So in the case of graphene oxide, because you have a lot of sp3 carbons that are attached to the oxygen functional groups, so when you excite the electrons from the valence band to the conduction band, when they decay, they do not decay because it's photoluminescence. So they decay to this defect state in sp3, and then from sp3 back to the valence band. And because of, as you can see that on the y-axis, the energy is not as much as if they decayed from the sp2 defect state. This is why it produces the red. But if it decays from the sp2 defect states, it's higher energy, which means actually this is why it's blue. We have a blue photoluminescence. As you can see, you can also the reduction of graphene oxide. Graphene oxide is red. It has a, let's say, red photoluminescence, whereas graphene oxide, reduced graphene oxide, has blue photoluminescence. What happens now if you remove, let's say, one carbon atom and replace it with boron, which is electron deficient? Which this is actually what is doped graphene is, the heteroatomic doping of graphene. So you take one carbon atom, or in this case, it's very hypothetical. This is theoretical. What happens is that because boron is electron deficient, so the Fermi level will shift below the Dirac point. So you'll have actually more hole doped or positively charged graphene in this case. And what happens in the case of, let's say, instead of boron, you have nitrogen, it will shift above the Dirac point, and the Fermi level will be above the Dirac point. And this is why it is, it will be actually negatively charged semiconductor. And of course, you will have the band gap in both cases. And this is how we produce basically P-type semiconductor with boron, and an N-type semiconductor with nitrogen-doped graphene. So this is a summary of how you can produce all the forms of graphene. And there are, of course, thousands of recipes in the literature for the bottom-up and top-down approach, but for the industrially speaking, and also the most favorable one, is the top-down synthesis. So you start from graphite, natural or synthetic graphite, and the most of it actually it's on the left. On the left, as you can see, you oxidize it first. So you break the PP interaction between the layers. So you weaken, let's say, the lattice structure along the C-axis, and you reduce the functional groups. And then you exfoliate because of you weaken the PP the van der Waals interactions, PP, and you exfoliate it. You produce graphene oxide, and this graphene oxide then you can thermally or chemically or electrochemically reduce it to produce graphene, or you can, let's say, functionalize it with polymers, and electroactive materials. In this case, let's say you can dope it, or you can decorate it with metal oxide particles and then reduce it. And the other path actually is by expandable. Again, back to the left, is by expanding graphite. So you intercalate it with like sulfuric acid, nitric acid, and then you pyrolyze it. So this is how you expand the graphite. And then the rest, liquid phase exfoliation in organic media, organic solvents. So this is it for the doping. Now for the doping of graphene oxide. So basically you intercalate it with the boric acid or urea, the boron, or this is actually to produce, as I said, P-type, positive type, or N-type, negative type, graphene-based semiconductors. So the intercalant, if you want, let's say, boron or P-type, you typically can use any boron precursor, in this case, boric acid. And in the case of nitrogen, you can use, of course, urea, because it's very cheap and industrial. So you do the intercalation, then you dry let's say the aqueous mixture of boric acid or urea, or actually both, if you want, let's say like co-doped boron and nitrogen, and then you pyrolyze the impregnated compound. And then you produce, as you can see, boron doped reduced graphene oxide, or nitrogen doped reduced graphene oxide, or in the case of the co-doping, you can produce actually both. Now to the porous materials. As I said, that the most interesting of them are the hierarchical porous carbons. So basically, there are plenty of recipes. Most of them actually utilizing hard templates. So basically, you use a hard template to template the macropores, the mesopores, and for the macropores, you typically, of course, you go for activation. But in the Knowskite project, we are using actually a very facile, very simple method, which is called ice templating. So basically, you take, let's say, an aqueous dispersion of colloidal silica, which has also glucose in it, and you take that dispersion or solution and you dip it in liquid nitrogen. So what happens is that, because it's flash freezing, so the ice fronts, they will propagate through that mixture as it freezes, and they will act as a soft template rather than hard template for the macropores. And then, as you may have already guessed, if you freeze dry it, lyophilization, you produce this beautiful structure. So basically, as you can see, these are the macropores. So you can see actually the freeze-dried glucose silica matrix has this very beautiful, smooth fishbone-like structure. And the walls of these macropores basically are the glucose silica matrix. So basically what you are seeing here, let's say the walls are basically glucose and silica, colloidal silica or silica nanoparticles actually. So the next step is to pyrolyze this. So when you pyrolyze it, but then you are still left with the colloidal silica embedded within the carbon network. So the next step is to etch them. So when you do the pyrolysis and after etching, as you can see that on the left scanning electron micrograph, the initially beautiful fishnet fishbone structure, it gets distorted obviously because of the pyrolysis and the etching. But you can see that you to a great extent you retain the original hierarchical structure as well as the mesoporous one. And you can see on the right is the transmit electron micrograph. You can see actually the mesopores, which are created because of the colloidal silica or the silica nanoparticles upon etching. And finally, even in these walls of the mesopores, then you introduce the micropores, which are less than 10 nanometers, by activation, whether physical or chemical by physical by CO2 activation, or chemical by using potassium hydroxide. So finally, the final material has macro, meso, micro porous carbon or hierarchical porous carbon. And even before activation, without macro micropores, it is also hierarchical because it has two levels of hierarchy: macro from the soft template, that is the ice front, and the meso from the colloidal silicon. So you can see the three levels of hierarchy of pore scales and their origins: ice fronts, the nanoparticles, which is the nanofiller, and of course, finally, from the activation. Notable properties about hierarchical porous carbons. First of all, they have very high specific surface area exceeding 1,000 meters square per gram. Second, because of their, as I said, the background is graphitic, graphene based, so they have very good electrical and thermal conductivities. Last but not least, they are chemically inert. Applications, why everyone is here today. So for the applications, first is, as I said, energy storage, and the three, let's say, energy storage mechanisms. On the left, you have the electrical double layer storage. In the middle, you have the pseudocapacitive charge storage based upon redox, let's say, sites in your material. And the last is the battery tap charge storage, which is purely, what do you call it, intercalation and redox based. So, and you can, and the top, actually, you can see the capacitance of the material. So if you want, let's say, like a glass of water and a jug of water and a big water tank or a big water bottle, dispenser bottle. So the first two, you can, in the first two on the left, you can charge them, you can fill them and charge and discharge them quickly. But as you can see that the capacitance is low. Whereas in the battery, of course, they have much higher capacitance, but their charging and discharging times are much longer than that. So depending on the applications. So supercapacitors, which is a unique type of materials, which actually combine the first two on the left, the electrical double layer capacitance and the pseudocapacitor, because from the redox sites. So they combine the non-Faradaic processes, the surface control, let's say, from physical chemical point of view, and also from the Faradaic processes from the fusion control kinetics, and also from the redox. And this is how the cyclic voltammograms for each case looks like, and also the galvanostatic charging and discharging profiles. You can see in the cases of the electrical double layer capacitors and the ones in the middle, the pseudocapacitors, the charging and discharging, so basically are much quicker than in batteries. But in the batteries, because of that plateau, you tend to, during the discharge especially, you can maintain charge for a longer period of time. So this is why you use batteries for EVs and not capacitors. Graphene. What about graphene materials for energy storage? Well, you can see actually that in the case of the reduced graphene oxide, as you may have imagined, that it is electrically conductive, so it's good. But the thing is that because it does not have the oxygen functional groups, so it doesn't have two things: the redox sites, which can enhance the pseudocapacitance from it. And the other thing is that because they don't have the oxygen functional groups, means that it is much richer than in sp2. And because it has more sp2, so the p orbitals, they will tend to promote the restacking along the crystallographic c-axis. So then you have the reduction in the double layer capacitance. Okay, what about the graphene oxide? Graphene oxide, yes, it has the oxygen functional groups, so redox sites, very nice. But what about their stability? They are not stable. So this is why after multiple cycles, you tend to lose oxidation, reduction, oxidation, reduction. You tend eventually to reduce graphene oxide, ending up having this rectangle like on the top of reduced graphene oxide, the shape, I mean, of the cyclic voltammogram. And of course, don't forget that in the first place, that graphene oxide is not a good it's not a good electrical conductor of electricity. it's semiconductor. So it's complicated. What about, one would ask, okay, why until now for lithium-ion batteries, okay, for the sake of argument, still until this very day, all the anode materials is still graphite and not graphene. Well, it's for actually the following reasons. First of all, compared to graphite on the first image on the left, you can see on the vertical axis is basically the ratio of the reversible capacitance divided by the irreversible capacitance in the first lithiation-delithiation cycle. You can see for graphite, it's much higher than graphene. Why is that? You have to check the x-axis, the xy. You can see actually that graphene has much higher defects and also specific surface areas compared to graphite. What does this have to do? We have to check one thing, is the formation of the SEI, the solid electrolyte interface, which is basically a soup. It is basically like a passivation film that forms with time of a soup of lithium byproducts that forms with time, as I said, but at the same time allows the shuffling of only one thing, the active charge carrier, which in this case is the lithium cations. So what's so different between graphene and graphite? As I said, graphene, because of the graphene layers are much exposed compared to in the case of graphite. So they have much higher specific surface area, which means that, I mean, from the surface surface phenomena, surface and interfacial phenomena point of view, they tend to promote, it's more induce the formation of the SEI, the solid electrolyte interface. And because of this, you have this reduction in the increase in the C irreversible. This is why you have the reduction also in the ratio. And in the image in the middle, you can see that in the case of graphite, so in the first, it's lithiation and the delithiation, it maintains what do you call it? More or less the same specific gravimetry, but as it's say with the cycling, you can see that eventually you have it has a very small hysteresis, voltage hysteresis between 0 and 0.4. Whereas in the case of graphene, initially we have a very low, almost similar, let's say, specific gravimetric capacity because of the, as I said, the solid electrolyte formation phenomena, but then it increases the specific gravimetry in the following cycles. But there is another problem, is as you can see that the voltage hysteresis takes place in a much larger window from 1 to 3, which is 2 volts compared to the 0.4 volts of graphite, which is very bad for, which means that actually graphene is a very bad choice because of this voltage hysteresis. It means it's very good, it exhibits poor energy efficiency as an anode material for lithium-ion batteries. But the only thing until now that in terms of as an anode material for batteries, the only thing that graphene has over the graphite is, as you can see, the ability to for sodium ions, especially for, let's say, like sodium ion batteries. If people who are interested, graphene is a good choice because of the ionic radius of sodium ions. They cannot be intercalated in graphite, whereas in graphene you can have them at all. So this is the only thing graphene has to offer. So what about the strategies for improving the linear density of supercapacitors? Fortunately, there was this honorable gentleman back in 2016. They come up with this summary of all the points that needs to be considered, or the aspects that need to be considered when designing supercapacitors. So from the electrochemical point of view, the setup, I mean, and also from the material point of view. From the material point of view, which is actually the aim of this presentation, which I'll be focusing on, there are 4 points: nanostructuring and the material's carbon, power density, and photovoltaic reactions. In the first case, for the nanostructuring, improved ionic pathway, which can be achieved by improving the pore size distribution, control of the pore size distribution, the tunability, and of course, chemical and physical activation. As for carbons, graphene-based framework, templated carbon. From the power density point of view, of course, because it will be graphene-based, so it has good high electrical conductivity, and you can improve, of course, the pseudocapacitance with doping. If this rings any bells, yes. Pristine and doped hierarchical porous carbons are indeed, based upon this, the next generation supercapacitors. And as you can see that people are rushing in the literature, and this was actually published last year. And you can see actually these are dominated with major pores, which are actually the most interesting type of pores materials. And so in this work, so basically they mixed coal tar pitch with polyvinyl butyral and cellulose together in aqueous mixture to plasticize it, and then extrude it, carbonize it, pyrolyze it, and then activate it to produce the microcarbons. And as you can see that you produce this porous graphitic structure from XRD. And from the elemental analysis also, you have the nitrogen and oxygen functional groups serving as redox sites for the pseudocapacitance. And from the nitrogen porosity point of view, you can see that the HPC20, which has the 20 grams of the polyvinyl, the PVB polymer, has the highest specific surface area and also total pore volume. And as you may have already guessed by now, yes, it yielded the best electrochemical performance. As you can see, the highest specific capacitance and also the charging and discharging profiles, and also for the electrochemical impedance spectroscopy point of view. As you can see that the HPC20 sample had a very nice balance between the capacitance and Warburg impedance, 45 degrees, and also the least material with the charge transfer resistance, since it has the smallest diameter. The next, apart from energy storage, fuel cells. So in this work, basically, they use HPCs as support for fuel cell electrocatalyst, to be more specific, as a proton exchange membrane fuel cells. So in this method, basically, you take the HPC, you impregnate it with an iron phenyl complex, and then you pyrolyze it. So eventually you produce nitrogen and iron heteroatomic doped HPCs. So in this case, as you can see that the orange sample is the iron and nitrogen doped HPC, and in the second case is basically the iron doped the KG600. It's a commercial carbon black, and you can see actually with HPC, of course, you have a much better pore size distribution than the carbon black. And this is reflected, of course, it will, of course, positively affect the electrochemical properties. So nitrogen, and you can see on the EDS elemental maps, very nice distribution of nitrogen and iron. And of course, as I said, that the HPC produced much better, yielded much better results than the carbon black. As you can see, in the figure on the top, on the right, you have a peroxide yield of 2%, which corresponds to actually a very nice high electron transform number, nearly 4. So finally, for the remarks, an interesting aspect actually of this kind of porous materials actually is to utilize SACs, small angle X-ray scattering. So as you can see that in the SACs, you can actually see in the wax above 10 nanometer inverse, you can see that which is wax, the structure. And then in the sacs, you can see the micropores and the particle-like properties. It's a scattering. So in the middle, between 1 to 10, you can see the micropores actually with sacs, and below 1, you can see both the particles and the mesopores. And you can see that the pores are created simply by the bending of the graphene, the constituent graphene stacked graphene layers, which is, if you remember the previous slides, in the XRD, powder XRD patterns, the 002 reflection was very broad. And the reason for the broadening is because of they tend to create the pores. They are the structural material for the pore walls. So, and stacks actually can give you a very insightful information into the pore structure, especially for the pore ordering, and also to quantify it. So this is actually the Taubner-Stray model for emulsions, which is recently being heavily used to characterize porous materials using sacs. As you can see, the intensity of the pores, scattering from the pores, is function of the Xi, which is the interpore correlation parameter, and the D small, which is the interpore distance. And FA is basically is fed as the amphiphilic parameter, which is like a disorder parameter. So if you have negative values of F, means you have very nicely ordered materials. If not, if it's positive, in this case it's 0.4, it means you have not correlation, but you have aggregation, not nicely ordered. And if it's above 1 and above, it means you have poorly ordered material. So in the Knowskite project, we investigated actually the effects of, we utilized colloidal silica particles for templating agents for the mesopores. And we examined the effect, we studied the effect of temperature. As you can see that in our case, the isotherms and the hysteresis is much better than in the previous recent works that I've just shown. And also the isotherms, they are type 4, and the hysteresis is type H1, which means they have very high pore ordering, no interpore correlation, no pore aggregation, nothing. And from the stacks also, you can see that it agrees with the nitrogen porosimetry. And of course, we utilized Python for the modeling, and you can see actually, I don't know if you can see it, the font is small, but we have, let's say, around D, the interpore distance is around 50.3, which is close to the 13.5. And also the disorder parameter, it has a negative value, which means you have very high dispersed pores. As for the deviation below 0.1 nanometer inverse, is because you have to check on the top that in the real space dimension, you start having particles above 10, 20, 30, 40, from 40 above. Yes, because this is now the scattering from the particle scattering. So this is why you have this deviation from the fitting. And then also in the Knowskite project, we investigated the effect of by model, if you can tune the mesoporosity. And yes, apparently it is tunable. So we considered two cases. So two types of colloidal silica particles with minimal size contrast, and also with we increased the size contrast. As you can see, it is doable. And also, interestingly, it affects, it yields a very interesting shape for the isotherms and also the hysteresis. In the case of, let's say, you have convoluted pore size distributions, bimodal pore size distributions, you produce a single hysteresis loop. In both cases, it's type 4 isotherms, but in the case of less size contrast, you produce one hysteresis loop, and that is type H2. Which means that you have pore ordering, or you have a no, and actually interpore correlation. In the second case, yeah, it is still type I4, but you can see it is basically a fusion of two type 1 hysteresis loops, like in the case of the monomodal mesoporosity, which means actually you have like two distinct mesopores, set of mesopores that are highly ordered and not not aggregated or intercorrelated. In conclusion, it is doable and it is tunable mesoporosity. So the next step basically is to, in the Knowskite project, we are planning to, with Sonia in Portugal, is to study their electrochemical performance for as supercapacitors, these type of materials. If you have any questions, please feel free to reach me. This is my email. And I would like to thank the organizers, Francesca, Claudio, and of course, Siavash, for enduring the pain and the agony to find the proper time and date for this webinar. And thank you all for your attention.
Thank you very much, Mohammed. So at the moment, I do not see any question, but we will keep looking at the Q&A section. And if we have questions for you, we will ask. So we can go on with the next speaker. That's Professor Vasilis Kyriakou from Groningen University. Vasilis?
Now
Yes.
you can hear me, I suppose.
We can hear you, yes.
Yeah, hello to everyone. Give me 1 second to share my screen.
Sure.
If you have too many screens, that's a problem. You try to find out
Yes.
which were. Now it's the presenter view. Now it's the correct one. Is that right?
Yes, but yes, now it's in full screen. Thank you very much.
So perfect. Thank you very much for this kind invitation. From my side, I will expand. I will go a little bit in a different direction. I will focus on perovskites and their applications for solid oxide cells. But solid oxide cells, not only for the hydrogen production, but something more, like reactors. And for that, due to their high complexity in catalysis as well, you need different properties, and we try to develop these mixed ionic electronic conducting systems. So first, a small introduction, because I don't know how many of you are familiar with Groningen, as Groningen, as it's called in the Netherlands, not Groningen. It's located in the north, where the university is at the top, I think, in the highest amount for Netherlands. We are quite far from the rest, because here the distance of a couple of hours is considered very far. This is the picture of the Zernike campus. It's the newest campus. We are located somewhere the Feringa building, which is here. This is a model, but now it has been almost finalized. This part. It's a beautiful city and a big university of around 40,000 students, and a great city to study. So for the students, that if there are students attending, it could be a good opportunity for your next steps. Now, in the Netherlands, we're quite dedicated to go to the energy transition, and some things are slow, but after they have been decided, I think the progress is quite impressive. So this is a scheme that I took from a platform for electrochemical conversion here in the Netherlands, and this is practically the plan for 2050. You see that the most of the energy will come from offshore renewable power, since the old routes through the natural gas of the north, close by actually here in Groningen, maybe you have heard it from the earthquakes problem in the past. So they have decided to go to a complete transition. However, as in all cases, when you want to rely your energy network also to renewables, there is a lot of questions raised in terms of the storage of the energy. And what we are proposing, or at least part of the solution, will be the chemical energy storage. You can think about it as a hydrogen, as methane, as ammonia, or whatever. But here in the middle, please see a very nice picture which you can compare an actual battery park, and the equivalent amount of energy can be stored in a 30,000-gallon tank for ammonia. So chemicals, or they can contain quite significant amount of power. That's why they are sitting in this left-hand side graph on top. in terms of they can have a huge range of power that you can store, and of course they have large discharge time. All of this is nice and interesting in theory, but the whole question is that how we can make this transformation efficient. My group, except of I'm focusing today on solid oxides, we're working also on alkaline electrolyzers as well. The solid oxides, they are a particularly interesting system at high temperature, because besides the traditional oxide ion conductors that I'm going to present you, there is also the protonic ceramic systems that they can operate at industrially relevant temperature, and this is what we try to do. So at the end, what we want to achieve is to have, for instance, a device that is looking like the one that you see in the middle, that you can convert abundant sources like steam or carbon dioxide or nitrogen with the help of renewable electricity into chemicals or fuels. Of course, if we have the chemicals, we know what to do with them, but upon any kind of efficient storage of in the form of a chemical or a fuel, we have also the route of re-electrification by practically operating the same system in reverse, like, for instance, a hydrogen battery. You could imagine it for stabilization of the grid or other uses. At high temperature, though, the things are a little bit more complex to what people have heard and have seen for electrochemistry, even at low temperature in liquid systems, because you have practically to integrate two fields. The one field is the electrochemistry, which has already their complexity, and the thermocatalysis, the traditional thermocatalysis. Therefore, it's a quite complex field. I will not hide behind my finger about it. People know it. So even if you want to test very small shells, small reactor cells, like the one that you see here of 25 millimeter diameter that we make here in the lab, still you need a whole system or similar to this one to be effective. So you need mass flow controllers, high temperature furnaces, the condensers, etc., etc. This type of systems, we connect it, and the exit of these reactors, always we're monitoring the products and the reactants when we want to bypass, with the help of gas chromatographs for online analysis, or even mass spectrometer for more qualitative kind of analysis. And since you have to make this very beautiful perovskite, which is also the topic of today's webinar and your project, the perovskites have a lot of chemistry, so we have the appropriate lab for doing the chemistry, but also we have ceramics, and they are still ceramics, so you need high temperature ovens and furnaces and all these deposition methods that we traditionally know. So today I'm going to focus on two different types. The first one is the high temperature one. The results that I'm going to show you and the concepts are, I would say, for temperatures between 750 and 800 degrees. Of course, they can expand to lower or a little bit higher depending on the application. I will focus on the co-electrolysis, not only hydrogen production, but synthesis gas production, hydrogen and carbon monoxide. Another interesting concept which has to do with the cogeneration by using methane-assisted co-electrolysis systems. And for that, we are using a MEIC perovskite, so mixed ionic electronic conducting perovskites. So ions can be oxide ions in this case, and electrons for this conductivity. And we discuss about the efficiency and the stability. And on the second part, I will discuss the newer area of protonic ceramic reactors or protonic ceramic cells, which they can have different applications related to electrolysis, hydrogen pumping, or process intensification by combining endothermic and exothermic processes. And the interesting thing with these systems is that they are operating between 400 and 650 degrees. Which is very close to several industrial applications. The interesting thing with these protonic ceramic electrolyzers is that most of their parts, even the electrolyte in this case, they are consisting of perovskites, and I will show you some of these categories. And I will close with a small summary. Starting with oxide ions, the concept of syngas production. First of all, why we're interested of doing high temperature synthesis gas production. So we start always from thermodynamics. As engineers, we should start from thermodynamics. If you see thermodynamics here, you see that the free energy demands for making CO2, converting it into CO and water into hydrogen, as you increase the temperature, the demands are decreasing. That means at the same time, the corresponding reversible potential, so practically the minimum amount of electricity that you need to provide, the minimum voltage, it's also decreasing significantly from room temperature to 700 to 800 degrees, where practically the solid oxides are operating. The other interesting thing here is that the demands for both splitting reactions, they are similar, which actually offers a system that by applying the same potential, you can co-electrolyze both CO2 and water. This is not the case for low temperature systems, for instance. How you do that? You practically have an oxide ion, a ceramic conductor. These are fluoride structure like yttria stabilized zirconia, and you have two electrocatalysts from the two sides of this membrane. On the fuel electrode side, we're supplying the CO2 and the steam, and you are electrolyzing tissue and hydrogen, and you are removing the oxygen. You pump out practically the oxygen from these two to a stream which we usually supply with air. So we enrich air with oxygen. Now, on the starting relate to materials from the fuel electrode side, you see here the typical cermets, as we call them, which is a combination of ceramic electrolyte and metal, which is typically nickel. Why you need a cermet for such an application? This comes quite in a simple way. We're talking about electrochemistry, and in electrochemical reactions, you need electron transfer, you need ionic transport, and at high temperature, gas transport of reactants and removal of the products. We have three phases in contact, and therefore we don't have a 2D area, we have a three-phase boundary. And this three-phase boundary is practically the contact that you see between the yellow and the blue parts for different contents of nickel oxide. So although very efficient for fuel cells, it's well known for many, many years, this type of ceramics. When you practically want to do some co-electrolysis under highly redox environments, you have steam, you have CO2, they are oxidizing, you're producing hydrogen, so you have a reduction as well. You can have these redox cycles that I'm showing you here in the first graph. So you have the nickel, which it's metallic, very nice interface. And then at some point, then your nickel or part of your nickel can be oxidized. It becomes larger in size. And then when it shrinks again from the reduction, you are practically losing your active surface for electrochemistry. So therefore, our solution is to practically move to mixed ionic electronic conducting materials, and that's in our case, it's perovskites. And the perovskite oxides, because they can have this intrinsic conductivity of oxygen and electrons, they can be quite useful. They are ceramic, so they are good for high temperature application, most of them. They are redox stable. They can have even caulking resistance if they have this mixed conductivity. And they can have significant catalysis if they contain elements, usually on the B side of good catalytic activity. What is the issue and what we want to improve is that the catalysis, although it's existing in perovskites, we're talking about oxides still. And their catalysis, in many cases, like in co-electrolysis, it's relatively limited. So we try to enhance these properties by introducing nanoparticles, so practically nanocatalysts over the MEIC. And this can be done in a simple way with infiltration of different nitrates. You can infiltrate copper nitrate, nickel, iron. There are different examples, cobalt or ruthenium. It can be done also with different deposition methods, like we showed some years ago with atomic layer deposition in this example. But we are particularly interested in exsolution. Why makes exsolution so interesting is that exsolution, you're practically inserting your active phase inside the oxide host, inside the MEIC, and this is released upon reduction of temperature, for instance, if you have the appropriate chemistry and stoichiometry and defects in your perovskite. A typical thing that we do, you can see it here, we're introducing deficiency at the A side. Practically, you have also more space for the ion to diffuse and precipitate after it reaches the metallic state. And you can create very beautiful nanostructure. upon you have the particles, what is their main advantage? We're talking about high temperature applications where you can understand you're working with materials, so you are aware of if you just deposit particles on an interface, on an oxide host, for instance, you will have significant agglomeration sintering of the particles at high temperatures. This is because they have shallow interface with the oxide host. But if you have a solution, your particle is already partially immersed inside the oxide host. And this makes it more confined. And according to these images that came from a paper back in 2015 from Dragos Neagu and John Irvine's group, they compare the nickel-X solution with deposited nickel on alumina, and they expose it to methane. And you see how much carbon has been formed on the surface compared to the more clear surface with the nickel. And the reason is because the carbon could grow between the oxide support and the nickel, while in the case of the X solution, the socketing nature of nickel sustain it in a very good state. Of course, there is some change in the size. Usually more X solution takes place, but not something that deteriorates the performance. This is a work that we did when we started working with X solution. We're really intrigued on seeing if it's possible to monitor in situ the X solution process. So some years before, we're in Lyon, they have a very beautiful environmental TM. We could manage to observe nickel-X solution from a titanate almost in situ, where we observe very beautiful, interesting things, like that this particle, for instance, is growing in hiatus and growing in hiatus periods in reverse. And this was published some years ago. So if you want to see more, please refer to the paper here. Another interesting thing is that we can have also flexibility, both in terms of the catalysts that you can exsolve, the particles, also in terms of shape, but also in the triggering method. You see in the first list of pictures here on the left, even bimetallic combinations of very active particles like cobalt, iron, iron, nickel, very interesting for catalysis, rhodium, that I will show an example later, or metal-metal oxides, heterostructures, particle shape depending on the reducing agent. So it's not the same if you reduce your material under hydrogen and you reduce under CO, or even under vacuum. Under vacuum, you had these polyhedral shapes. Here we had some spherical shapes. This is under CO. So depending on the perovskite, the element that you want to exsolve, all this can affect your shape. And besides the traditional, let's say, a reduction by hydrogen or by gas environment, you can achieve very beautiful results very fast if you apply a very high amount of voltage for some seconds. You see here the nickel-X solution after voltage imposition. And we also demonstrated how you can do that with plasma, because back at DIFER, when I was doing my postdoc, there they had a very beautiful, we were doing beautiful science with plasma. And since this is an environment that can be reducing as well, we thought, why not we expose our materials to nitrogen plasma, for instance, that it's typically inert if it's not in a plasma shape. And we could achieve this amazing heterostructures. These are nickel particles on a titanate. We even did further analysis with a transmission electron microscope, and we found out there was nickel-X solution in both sides, but at higher population. So the plasma has its own advantages. And therefore, if you are interested in learning more, please refer to this publication or contact me. Yeah, so now passing by to another very interesting application of the co-electrolysis. Since we cover some things about X solution, what is happening and what is the advantage of X solution in co-electrolysis, for instance? For that, we started by making a half shell of supported on the ceramic electrolyte, Scandia stabilized zirconia. And we had an LSCF GDC based electrode on the second side. and we only replaced the fuel electrode. In one case, we tested the titanate perovskite with nickel solution, and the second example was a nickel YZ. So we printed nickel YZ, and we did the test, and we operate the cell in reversible mode. For the people that are not familiar with reversible mode, practically you are co-supplying here on the fuel electrode side hydrogen, water, and CO2, vapor and CO2, and air on the second side. If the polarity allows it, so if you are at positive currents, you have fuel cell operation. So spontaneously, the oxygen ions that they are created on the cathode, they go to the anode, and they are finding your hydrogen, and they are oxidizing it by producing power at the same time due to this spontaneity. On the left-hand side, so if you go to electrolysis, let's say potentials, practically you have to pump the oxygen from the water and the CO2 to the air side, which is, of course, energy consuming, and therefore you have electrolysis. In this case, you're producing syngas, but you're consuming electricity. What is important to see here is that the performance that we got for the perovskite in a similar system is comparable in all cases, which was very good for us initially and very important, although we're more interested in the qualitative comparison. The results that I just showed you, hydrogen was co-supplied. That means that the hydrogen could be sustained in a metallic state, and therefore we couldn't see the effect of the coarsening that I showed you some slides before. What happens if we are removing the hydrogen? There is no safe gas in the environment of the cathode. If you just co-supply water and CO2, that will allow you that if you apply the voltage, you can even control the ratio maybe of hydrogen and CO. With the blue curve is the titanate, and with the solution, and the gray curve is the nickel YZ. Of course, when you have the nickel YZ without the safe gas, you start having these large clusters of nickel oxides that we monitored and we found in the SEM. While interestingly, for the titanate with the nickel solution, we observed that we had even more nickel nanoparticles closer to the interface with the electrolyte after the finish of the 2-day test. So this shows that if you want to really control the ratio of the syngas production, you have to avoid the safe gas, and the use anymore of CERMETs, it's not possible. So we have to turn to effective mixed ionic electronic conducting materials like perovskites in that case. And a solution can also help in that direction by enhancing your catalytic reactions. I will go a little bit further. This is a concept of co-electrolysis. You see it here with a dark gray on the end. And here I have plotted, let's say, what could be the electrical power consumption possible and what will be the viability of your products. In traditional, let's say, electrolysis, you want to do something which is very difficult. You want to pump oxygen from a small partial pressure of oxygen, of water and CO2, to a large one, which is the air on this side. That means that you have to pay a significant amount of electricity, which reflects in these to above 1 volt necessary for even at high temperature. What happens if you substitute the air on the anodic side with a fuel that it can be cheap or can be renewable, like one example can be methane. It's not only natural gas that contains methane. At the anodic side, if you supply this methane, if your catalyst allows it, you can oxidize it to CO2 and water, for instance, and then you reach in this blue curve. This is the free energy, the energy demands. You see it with the blue curve here. It's at least 1 volt lower, and at temperatures above 650, you see that there is even a region where practically no electricity is required. How this happens is because the system, and solid oxides are unique systems to do that, they can exploit the heat content of your fuel to convert directly to electricity, to electron transport, that they are helping in the electrolysis of CO2 and the steam. Of course, this is very nice as a concept. We have maybe even power and syngas cogeneration, but you are producing CO2 and water again. So what we said some years before was, okay, what about of actually making syngas from the partial oxidation of methane at the anode? This is also a spontaneous reaction at high temperature. So if you do the calculations, this will give you this green line that you see here. And the nice thing with this, in terms of electricity, that can even be even more spontaneous at high temperature compared to the complete combustion. This creates a very beautiful system in which you have practically a system that can produce syngas at both sides, cathode and anode of your solid oxide cell, like a catalytic reactor, and even doesn't need electricity in theory. Of course, these effects are according to thermodynamics. The question is that what is happening in the actual system, and if you don't take into account the kinetics, you're not going to see any of these effects. In order to see that, we had to make an even more effective X solution. With the same titanate, we replaced the nickel with rhodium solution. First, two interesting stuff happened from that. The first is that we had an amazing nanostructure of rhodium solution. This is the picture by our calculation was around 2,000 particles per square micrometer. But other samples that we have in the same paper, we reached above 10,000 particles per square micrometer, huge population of around 2-3 nanometer size. Very beautiful structures. And of course, if you have rhodium solution, it's very, very effective. And this helped us to prove the concept. You see here with the blue curve, and this is the voltage required, cogeneration region, practically short circuit region on this line, and electrolysis. If you take the best perovskite out there, like a double perovskite, like SFM, like strontium iron molybdenum, and you check the concept like was in literature, we observe this curve. Okay, there is some effect, but the currents are very, very small. And particularly if you are not reaching close to 0.9 volts, you are not producing significant amount of synthesis gas. However, with the rhodium solution, you see that we have an almost linear curve up to 1 volt that practically help us to demonstrate cogeneration of electricity and syngas at the same time. Here, no electricity is required. So we had here around 0.4 ampere without practically consuming any electricity. The voltage was 0. And then for electrolysis, of course, it's still more efficient. What this reflects in synthesis gas, you see it here. You see this is the amount that we could produce with the rhodium, and this is the amount we produce with SFM. That demonstrates clearly that we can have up to 6 times more syngas production compared to the conventional perovskites that we know. So this demonstrates that such concepts, they are possible, but we have to and we have to develop very effective mixed ionic electronic conducting perovskites for such a role. This leads me to the second part of my presentation, the proton conducting materials. The beautiful thing with proton conducting materials is that since they are conducting protons and not oxide ions, their conductivity, the activation energy is less required for transporting practically an ion through a wall, because this is what we try to do through a ceramic. And therefore, they can operate at temperatures much lower compared to what we know traditionally for solid oxides. The first report came back in the 80s from Professor Iwahara's group in Japan, where they created a hydrogen pump, practically, by using a perovskite based on strontium and ceria. So strontium on the A side, ceria with other metal like yttervia, it was the best one on the B side. After that, there is there was interest, but not significant rise in publications the last years. However, in the last, I would say, 10 to 15 years, there is a huge increase in the number of publications in this field and in very good journals. We have different materials that they can, there more that they have demonstrated to have protonic conductivity. Some of them, of course, and the most important are perovskites, but there are also pyrochlores, and there is also these tungstates, like lanthanum tungstate is very popular as well, with very good conductivity at intermediate temperatures. The material that we are focusing and we are developing as well in our lab is the barium cerium zirconia yttria, typically also doped with yttervia. So it's a quite exotic configuration with a lot of elements, but it's really worth it, the effort. Now, in terms of the advantages of such system, well, we'll start with protonic ceramic fuel cells. If you have a fuel cell, just for you to remind you, it's you're feeding the hydrogen at the anodes, and then you at the cathode you supply the air and the oxygen ions in a traditional solid oxide fuel cell. It's burning your hydrogen. In protonic ceramic cell, it's the opposite. Actually, the hydrogen in the form of protons is the one that is transported to the cathodic side, and this gives a big advantage in terms of avoiding any dilution of your fuel. So that's, I would say, the most interesting thing. It has been demonstrated to have significant fuel flexibility. And the other nice thing is that if you go to temperatures below 600 degrees, you can even use cheaper ferritic steels for interconnects in such a system, which is quite important. And of course, as you decrease the temperature, you have also faster startup. Other applications, they are involving, of course, hydrogenations and dehydrogenations, or hydrogen pumping, as we call it. So they are hydrogen pumps. Of course, if you have a ceramic membrane, so you have two different chambers that they are sealed, you can have a mixture of hydrogen that you can extract from any moment. So there are different applications. One very interesting one for the future has to do with the biogas steam reforming. You are producing, let's say, if you supply biogas or ammonia on this CERMET or nickel BZCY, the material is helping as a catalyst. You are producing hydrogen, which can be converted to protons, and you can extract pure hydrogen or almost pure hydrogen on the second side, on the cathodic side in such case. That's one of the applications. It has been demonstrated for biogas, for ammonia, for hydrogen extraction from ammonia, which is particularly interesting. Or there is the example that you see on the right-hand side where you practically dehydrogenate your alkane to alkene. I have seen very interesting papers related to the conversion of methane to benzene, because still you have to create radicals in such case, benzene and hydrogen, or ethane dehydrogenation, or even propan dehydrogenation. Very interesting aspects. One example that we did back when I was in Greece several years ago for protonic ceramics was the steam methane reforming, where the group of professors Toukidis were the first ones to demonstrate that you can practically use them as hydrogen pumps. And the steam methane reforming is a typical example. It's a low temperature steam methane reforming. As you know, it is thermodynamically limited, so it's an equilibrium reaction. It's highly endothermic. And the steam methane reforming, you have to do it usually in industry like 750 to 800 degrees or even higher. That means that if you want to decrease the operation temperature of the steam methane reforming, then somehow you have to either extract one of the products. And one of the products that we're interested in is hydrogen, and we could extract it. So for instance, if you have, let's say this, I have plotted here the methane conversion and the CO2 selectivity to the steam carbon ratio. You see here that we had the electrode on the inside, this nickel-based electrode, is a very good catalyst. And that's, of course, it makes sense because nickel is the catalyst, the industrial catalyst for steam methane reforming. So you can achieve very good very good conversion here. But the interesting thing happens when you are starting pumping the hydrogen out of your anodic site. As you are pumping, the methane conversion is increasing. And of course, it doesn't violate thermodynamics. As you are pumping the hydrogen on the second side, according to Le Chatelier's principle, you are shifting the equilibrium of this reaction to the product side, and that means that you can extract even more hydrogen and have higher methane conversion in expense of electricity. It's another factor that comes there. Several applications. This is a recent review that we prepared with my postdoc and my PhD student on protonic ceramic reactors. As I told you in the beginning, we are particularly interested in using the solid oxide cells, either proton conducting or oxide ions, as reactors. They have huge potential. It's not the traditional view that we have only to produce hydrogen or power out of them. I think they have much more potential to be unlocked. To do that, for instance, if you want to combine, see the case A, if you want to combine, like we try to do now in a European project, the co-electrolysis in a protonic conducting cell, but this time, if you operate at lower temperatures, like 400 degrees or 350 degrees, then you can go to products beyond synthesis gas. You can even produce something like methane or another type of hydrocarbon, or even olefins. This is the project that we want to achieve, what we want to achieve in the project. So the key here is to decrease the operation temperature. However, the problem that we mainly have, except of the catalyst at the cathode that I'm not going to touch today, is the water splitting. Here, the environment is different, and the reaction is much more complex. So in traditional solid oxides, your water splitting takes place at the cathode. In this case, the water splitting takes place at the anode. So you have to oxidize the steam into protons and oxygen that evolved from the electrode. So if you want to do that at high temperature, you cannot use metallic metals. So you have to go to perovskites as well, or at least some other type of mixed conductors. Perovskites are particularly interesting because what we want to really, what is the mechanism requires is that you have to absorb the water, the steam, and then you require vacancies and oxygen of the lattice so you can create the protons that they will be diffused through the electrolyte. So this that you see here, the 2OH minus, practically is proton, which has been trapped around an oxygen in the lattice. And this will move, this is the protons that they move. They don't move like separate protons in this type of conductors. Practically, they are hopping from oxygen to oxygen. That means that the water uptake properties, oxygen vacancies, and the mixed conductivity is very important for OER in such case. And to do that, you need usually triple conductors, triple phase conductors of oxygen, anions, protons, and electrons. And some of the perovskites have been observed to have these properties. One of them that we could find in literature is a praseodymium A-site, nickel cobalt B-site perovskite, single structure. We tried this material, except of the nice performance, we saw that it has a lot of potential for further improvement. And with rational doping, so with something simple, you can enhance the properties. From one side, if you want to do electrolysis, theoretically, if you add calcium, that is a 2+ oxide in praseodymium, on the A side, you could create some extra vacancies in your structure, and at the same time, you can enhance also the water absorption properties. So my student, PhD student Nanan, she tried to synthesize materials, but even with small amounts of calcium doping, she observed some minor impurities in the X-ray diffraction, not at the level that we're not going to test the material. We checked also with SCM, and we found that we couldn't see any of these impurities, let's say, like secondary phase on the surface. Most likely, we could create some kind of multi-layered oxide. But the interesting thing happened when we tested or we exposed it to reaction conditions, where practically we even observed exsolution. And we're still trying to understand the phenomenon on the exsolution. But the first thing that we had to do when we observed this very high population of particles on our electrodes was to first understand what they are. And in this case, it's not nickel or cobalt from the B side. The results and the analysis show that we have praseodymium oxide. So this time the exsolution comes from the A side. And that makes also sense. We have a highly oxidizing environment, so you couldn't expect that the nickel and cobalt, maybe they will exsolve. You would expect that maybe the A side. That's still under exploration. So I cannot tell you too many things, but the interesting thing is that the addition of calcium also enhanced the amount of exsolution, actually double the amount of particles. There are so many things that we still can learn from such applications and such materials because they have very beautiful and rich chemistry that we are still, let's say, we're only scratching the surface. This is
Professor,
yes?
sorry, I must ask you to speed up your presentation because we are already over 5 minutes, but don't worry.
Okay. So sorry for
yes,
that.
just to tell you.
Yeah, so, yeah, okay, it's 35 minutes. Yeah, I will. It's still a couple of slides more. That's it. Yeah, so this is a proof that the praseodymium is the one that is exsolving praseodymium oxide. You see also with the STM and EDX that practically is praseodymium and cobalt oxygen that they are on these particles. In terms of performance, because I think that's the interesting thing in terms of application, and I will close with that, it's that if you deposit it in a single cell, this is a small diameter cell, 20-25 millimeters. Even with a small addition of calcium, for the reasons that we just explained, and the more exsolution and the calcium addition, the currents were doubled. And I don't know how familiar with current densities in these systems and solid oxides. However, to achieve at 600 degrees, around 3 ampere per square centimeter, it's significant, particularly if you're talking about 1.4 volts, where a typical electrolyzer would work. So this has still work under preparation, and yeah, it's I would say a very interesting effect. Now this leads me to the summary. I think there are some messages that I would like to leave you with. It's first of all that at high temperature in solid oxide cells, even both type of conducting cells and ceramic cells, we have to see them as reactors. But at high temperature in solid oxide cells, we can only target products like hydrogen and carbon monoxide with high efficiency. We need the MEIC electrodes as well there, because at these high temperatures and with so high complexity, this is the best thing that we can do. And then there are the upcoming protonic conductors at lower readiness levels, which has also their own potential because they can unlock this intriguing area for electrochemistry, which is the intermediate temperature range. Okay. And I will close with that. These are some acknowledgements for the funding of this research, which also have to do. And of course, thank you very much for your attention. And if you want any more information, my email is this one. My apologies. I thought that I had arranged the time very well, but I didn't. So sorry for that.
Don't worry. Thank you very much. So we can proceed with our next speaker, Dr. Annette Trunschke from the Max Planck Gesellschaft. Annette? We cannot hear you. Okay, so while we find more about the issues of Dr. Annette, I don't know if we want to proceed with the next speaker, Mark Torrell from EREC. Mark, are you with us?
Yes, here I am.
Okay,
Can
Mark,
you hear me?
sorry for the change in the plan, but okay. We'll try to fix whatever issue Dr. Trunschke has. So if you can share your screen, we would go with your presentation and try to recover Dr. Trunschke.
Okay, if this is okay with Dr. Trunschke, it's okay for me. And actually, the topic,
we can see it.
Yeah, you can see it. So actually, the
yes.
topic of Professor Basilis is quite linked with what I want to present today. So I will put it in presentation mode. Let me. Can you see in presentation mode?
Yes, thank you very much.
Well? Okay,
yes.
So as I was saying, last presentation was about somehow the materials for solid oxide cells technology on the proton and oxygen conductors. My talk is on the same topic, on the same application, but more on the macro scale. Let's say that I will talk about the manufacturing the processing of this ceramic technology, these ceramic materials that we need for the solid oxide cells technology. I'm Marc Torrell. I'm coming from the Catalan Institute for Energy Research in Barcelona, Spain. So I think that all the audience is quite familiar with this hydrogen strategy that we have in Europe. Europe bet for the hydrogen technologies for the decarbonization of the different sectors of our society. And well, I put here a very simple scheme of which is the role, or the general role of these two main devices that we are using. Say the fuel cells are taking the hydrogen to produce power and also heat, and the electrolyzers taking this water to convert it through the use of the storage of the renewable energy to hydrogen, and from this hydrogen, the direct use of this hydrogen, or going for different routes to generate synthetic fuels. For these two modes of operation, fuel cell and electrolyzer, we know that we have mainly three different technologies, named the alkaline technologies with the typical liquid electrolyte, anode and cathode, transporting OH ions. Then we have the proton exchange membrane technology based on a polymeric membrane with a cation or proton conductivity, proton transport, and the solid oxide cells that can that operates by an ionic transport membrane, basically a dense ceramic with all ceramic constituents. So both electrodes and electrolyte are ceramic materials. We can find them in electrolysis, but also in fuel cell mode. Today, I will focus my talk on the solid oxide electrolysis cell. That is the topic that I'm working with in the institute. So as it seems, the audience is already familiar with that, and Professor Vasilis has presented it very clearly and deeply, but these devices are constituted mainly by 3-4 ceramic layers. We have the oxygen electrode that in fuel cell mode, we have the reduction of the oxygen to the oxygen ion that then it's transported by the electrolyte membrane, in this case, typically doped zirconia oxide, that sometimes, and depending on the electrode, needs the use of a Syria barrier layer to protect from the reactivity that comes from the interdiffusion of the cations from some electrodes, mainly perovskites that can react with the zirconia and generate isolation phases. And then the fuel electrode mainly constituted by nickel YZ cermet. In this fuel electrode, we have the oxidation of the hydrogen and the production of this power generation. In simple words, these devices can also operate on electrolysis mode, on a reverse mode, where we store the renewable energy or any kind of energy as hydrogen by the reduction of water and the evolution of oxygen. As it has been also mentioned, these electrolyzers in high temperature electrolyzers based on solid oxide can also work in co-electrolysis mode, where we reduce mixtures of water and CO2 to generate this syngas that it's at the end valuable for itself, but also the precursor of some all the synthetic fuels that we can generate by a catalytic process. Knowing that, I want to add that I think that it has not been mentioned that these devices can be structurally made by an electrolyte supported cell, where the electrolyte is the more mechanical robust layer on this device, or fuel electrode, or known as anode supported cells, where this robustness comes from the fuel electrode, from the anode in fuel cell mode, or the metallic supported with the porous metal support. All these options, all these architectures are manufactured or are stacked to achieve the powers, the capacities that we want to have to implement these technologies in what we call stacks. Here you have different examples of the different commercial stacks of the main actors that we have today in Europe. Probably you know some of them: Sunfire. In Germany, Solidera. We have here also Elcogen or Ceres Power. They use these different configurations that I was speaking about in the last slide. But at the end, what we have is the cell itself, which is a ceramic cell constituted by these two electrodes and the membrane electrolyte in the middle. And we need this, what we call the bipolar plate or the interconnect, that it's a complex metal sheet that it's interconnecting cell by cell to achieve the power that we need. As you can see, there are heavy pieces, complex pieces that has to be mechanized or done by powder metallurgy or stamp or by different processing. We have to have these interconnects connecting the different cells. What is the ceramic part? It's mainly done in the conventional technology by tape casting. We have here a simple scheme of what it's tape casting based on a doctor blade that it's making a tape of these green ceramic pieces that it's rolled and then sintered to do mainly the fuel electrode and electrolyte, and go sintered, and then we screen print the rest of the layers, mainly in the oxygen electrode, to end with this type of cells that we have here, typical solid oxide cells, fuel cell or electrolyzer. Okay, so this technology has been evolving thanks to the efforts of all the community on the electrodes, as we were seeing in the last presentations, the electrolytes, but also the stacking engineering, and also on the system level. The technology, when we compare on a fair comparison with the other technologies, with the alkaline and the protonic exchange membrane, we can see that the main difference is the operation temperature. Solid oxide cells operates at temperatures in a range between 500, 600 to 900 degrees, while the other technologies operates at much lower temperature. And this gives to this technology certain thermodynamic and kinetic advantages that makes, if we look to a real advantage, or a real step beyond on the consumption in electrolysis mode of the power to generate, in this case, a kilo of hydrogen. So in alkaline technology, we're between 50-55 kilowatts hour for the generation of 1 kilo of hydrogen, 50 in the case of proton exchange membrane, while in solid oxide we can reduce this to 38-40 kilowatts hour per kilo of hydrogen. This is a real advantage, but we have other drawbacks, and some of the drawbacks of this technology, or one of the main ones, is the mechanical robustness of these ceramic pieces that makes at the moment very difficult to operate them under pressurized conditions, which is quite important for the downstream processes. So if we want to use this hydrogen for storing, we want to use this hydrogen for the production of any other added value or for any industrial process. Usually this process goes with pressurized inlet. So the fact that we have to pressurize the hydrogen on the solid oxide cell after the generation gives us a disadvantage compared with the rest of the technologies. Another problem is the starting time for the fuel cell applications. For instance, we need to heat up the technology to this high temperature, so this takes some time, and this is also related with the mechanical stability of the ceramic pieces, that it's limiting their application to the stationary sectors, unlike the PEM technology, for instance, that it's also used in the transport. So giving this framework and giving this introduction to the different fuel cell and electrolysis technology and focusing on the solid oxide cell technology, well, here I think that this plot already appears, where we can see that for the same production from the same current density, we have much lower voltages for the solid oxide technology. That means a more efficient technology, as we were commenting. So recovering what I was saying, once we have this frame and this introduction to the different technologies and the way that has been conventionally fabricated, the ceramic pieces, I would like to explain you today our new approach, our disruptive manufacturing processing for this technology. In our group in Barcelona, here in Barcelona, in the Institute of Energy Research of Catalonia, we in 2016, we acquired the first additive ceramic manufacturing machine, an industrial machine able to print functional ceramic. We have been exploring the different additive manufacturing technologies for the processing of ceramics, but basically we have been working on the extrusion freeforming, or what it's called direct inkjet writing, and also on the stereolithography. With these technologies, we can improve the technology in different solid oxide technology in different scales, from the shape complexity and the centimeter scale, but also a hierarchical complexity on the scaffolds, microstructures on a lower scale and the range of hundreds of microns, and also the material complexity on a more smaller scale. So considering this, we focus on the use of stereolithography technology to generate our solid oxide cells. The process, I think that I will try to increase the volume. Okay, here we have the processing of this stereolithography. We start by the design coupled with simulation. You will see that in ceramic additive manufacturing, we have infinite possibilities on the geometry. So we try to couple our first design step with simulations to know that what we are proposing is worth and it's giving us an advantage compared with the conventional planar technology or planar architecture of the solid oxide technology. And then we formulate our pastes. Here is for printing mainly the electrolyte side of the electrolyte piece of the technology. So we formulate different zirconias, doped zirconias with different doping cations for having the different electrolytes. Then we go to the 3D printing step by this stereolithography. Here you can see a video that it's showing how the stereolithography works. It's a technology based on a light source. This is a laser that it's curing a light curable, visible in the range of UV visible. It's a photocurable polymer that we are curing layer by layer by this laser. What you can see here in the video is just based on polymeric printing, but what we are doing is to, in this formulation step, to adding to this slurry the ceramic load, in this case the electrolyte of our solid oxide cells. Then we have a cleaning step, and afterwards we have the thermal treatment. As I was saying, our manufacturing technology, it's based on a mixture of photocurable polymer with the ceramic load. So at the end, what we have, it's a green piece that is happening with the tape casting or the conventional manufacturing technologies. So then we have to make a step called the binding, that is to burn out all the polymeric part of this green piece to end with only the ceramic. Of course, after the debinding, what we have, it's like, let's say, a sandcastle. We have just the ceramic, but it's not densified. And then we have another thermal treatment, that it's the sintering itself, where we achieve the final densification of our pieces that we need, achieving densities of 98-99% on these electrolytes. Here you have a scheme of how is this stereolithograph machine, the laser, the printing platform, and the scrapping. So layer by layer, in layers of 25 microns, we can grow this electrolytes for our solid oxide technology. With this and with industrial stereolithography machines, we can print different materials, mainly alumina and zirconia, and we are applying it for generating complex shaped catalytic monoliths that can then be functionalized with the different catalyzers for different reactions. We can also print monolithic reactors itself, where we can put any feature that we desire for the heating, cooling, temperature control. As you can see here, different channels, different holes for adapting our catalytic reactor to any requirement of the specific reaction, but also large area electrolytes, large area solid oxide cell membranes with complex designs, tubulars for solid oxide cells with complex design, but also for membrane catalytic reactors, other monolithic devices. This one was dedicated to the electrolysis. Okay, a more complex device, a more compact device, and a monolithic, saving all the part of the sealing between the cells. So a monolithic approach. And here some corrugated button cells that we have been scaling up to the stack level. We have also some activities on our solid state batteries that we can also print the electrolyte materials by this technology, giving some materials, some geometrical complexity, and giving some advantage to the application. Okay, so the idea today is to explain the process that we have been following for the scaling up of these solid oxide devices based on the use of additive manufacturing, and which have been the advantages and the challenges that we have been facing. So we start from the button cell to the stacking cell. So at the beginning, we start with a very simple approach. So what we wanted to know and what we wanted to prove is that our processing was able to generate electrolytes as good as the ones generated by conventional technology, by tape casting. So this is a printed button cell of 2 centimeters in diameter, flat cell that we printed in our machines, and then we sinterize at 1450 degrees. And as you can see, at the end, we achieve, as we desire, a very dense electrolyte. To prove the conditions and to prove the applicability of this electrolyte, what we did is the measurement of the ionic conductivity of this electrolyte and compare, as you can see here, with the ones in literature performed by tape casting. As you can see, we have almost the same behavior and the same ionic conductivity. This is the ionic conductivity per T, plotted by the inverse of the temperature on an Arrhenius plot. And here you have the activation energy of this electrolyte. In this case, 3% dope zirconia by yttria. And we have exactly the same values that we expect for the conventional electrolytes. The same we did with the 8% dope zirconia, actually having the same behavior, the same values of ionic conductivity. So at the end, we prove that in terms of material, the electrolyte behaves exactly the same when we print it even in a flat cell than what we have in the conventional manufacturing. Then we functionalize with the typical state-of-the-art electrodes. In this case, it's nickel YZ and an LSM, lanthanum strontium manganite, with a quite thick electrolyte, but it was just to prove the concept. And we can observe that we have the expected theoretical open circuit voltage without applying any current, just for the difference on the potential of the different atmospheres. We have air in one side and pure hydrogen in the other, and we reach acceptable open circuit voltage at the operation temperature. And then we had already what it's known as a full cell with the electrolyte and both electrodes, and we perform the IV curve. Here you have the current density as a function of the voltage. This is the open circuit voltage that we have seen in the previous plot. So we ensure the gas tightness of these devices, and we could perform this IV curve, achieving up to 100 milliwatts per square centimeter at 900 degrees, which is not very high power density, but we have to consider that these were the first trials, and we were using a 330 microns thick electrolyte. So we wanted to progress on that once we have the proof of concept, and we start putting some complexity in our electrolytes. Here we print the honeycomb with the idea of putting some mechanical resistance on the membrane, helping to the reduction of the membrane inside this honeycomb and reducing the thickness of this electrolyte that, as you know, is one of the main contributions to the resistance of these devices. Besides this, the fact that we are putting a honeycomb on top of this electrolyte, it's also somehow increasing the area of this electrolyte, so the active area of the cells. And we can see this is the previous plot on the flat membrane compared with the plot that we achieved on the honeycombed printed electrolyte once as functionalized by nickel, YZ, and LSM. And you can see that we have small increase on the power density because of this reduction on the thickness on the membranes inside, and also due, following the simulations, also due to some activation of these nerves as an increase of the area that we have in these button cells. But of course, this is we need to scale up because this is just on button cells. So we try to transfer this to a larger area cell, and this time already with 8YZ, so a better ionic conductor, a better electrolyte for our solid oxide cells. And here you have the image of this thinner and 16 square centimeters large area solid oxide cell. Here we have the cross section. You can see that apparently the electrolyte is exactly with the same microstructure that you can see in any tape casted cell, and the interfaces between the air electrode and an oxygen electrode with electrolyte, it's the conventional one since it's functionalized after the printing. So here some more IV curves. Here you have not the current density, but the total current, and on top you have the current density of these cells operating as a fuel cell at 850 to 950 degrees that we could achieve 3.5 watts per cell in this case on fuel cell mode, and up to 5.5 amps in total. It's equivalent to 350 milliamps per square centimeter in the electrolysis mode. We perform also some degradation studies during more than 1,000 hours. No surprises, and this no surprises comes from the fact that we are using state-of-the-art materials. Okay, our approach has been, I think, that quite disruptive in terms of the manufacturing technology, in terms of the geometry of these cells. But at the moment, we wanted to keep the state-of-the-art materials to ensure that the different things that we were studying were coming just from our changes on this processing more than in the materials that we are producing and studying in other activities in our group. So one of the limiting factors clearly was the thickness of these electrolytes that we print. So one of our focus has been the reduction of this thickness and trying to put it on a larger scale cell. Here you can see already a 25 square centimeter cell. It's 7 by 7, counting the frame, but the active area is 5 by 5. And we could achieve already, our PhD student achieved already thickness below 80 microns on large area cells, and even lower than 50 microns on button cells. And to give some mechanical resistance to these membranes, we are adding here some features, some nerves that withstand this thickness on the membrane. So all in all, the thing, of course, you have 65 microns on the membrane, but the thickness of the nerves are a little bit thicker. Here you have the example where we have nerves in the 50% of the area. So half of the electrolyte is with nerve, half of the electrolyte is without the nerve. We have also some tests on 25% of the area covered by the nerves, and it's also working. So we are progressing now to reduce this thickness and achieving better results. Here in button cell, 8YZ already, 900 degrees. We have 1 batt per square centimeter, which is already quite a nice result. Achieving, let's say, the state-of-the-art values or the key performance indicators of the technology done by conventional technology. We can achieve the same by this 3D printing approach. Also in electrolysis mode, surpassing the 750 milliamps per square centimeter at 1.2, 1.25 volts, which is the typical operation point of the electrolysis, the high temperature electrolyzers. Also in large area cells, so this 25 centimeters square, so mid area size, this time with 3YZ, which conducts a bit worse, but also having quite remarkable results at 0.7. So we already have this more than 6 amps and achieving these 5 watts per cell in fuel cell mode. And this on electrolysis mode, it's converted in around 320, 350 milliamps per square centimeter. So quite reasonable results that prove that the advantages of putting some complexity on these cells can be the way to improve some of the problems that we were seeing at the beginning in this comparison table, because we are adding some mechanical resistance to this technology. Besides the geometrical complexity, we wanted also to have some flexibility on the materials, the electrolyte materials that we could print. You have already seen that we were able to print zirconia doped by 3% of yttria, also doped by 8% of yttria, but we have also some results already in the use of Ytterbium Scandia doped zirconia and also Scandia doped zirconia, which is multiplying the ionic conductivity. Here you have an Arrhenius plot of the different typical electrolytes. These 4 are by 3D printing. So these lines that you can see here are the different 3D printed electrolytes. 8YZ, Ytterbia, here you don't have the 3YZ, but it's a bit worse than this 8YZ, 8YZ, Ytterbium Scandia, and also Scandia doped zirconia. And in the dashed lines, you can compare with the literature, with the reported values for the conventional Scandia zirconia, 8YZ, or other electrolytes used in or reported in the literature. So quite happy on that. This means that once we can scale up these materials, the printing of these materials, we can multiply and multiply our performance either in fuel cell mode, in electrolysis mode. As you can see here, we multiply by 3 the ionic conductivity from the 8YZ to the Scandia zirconia. So here are some IV curves proving already this capability of printing new electrolytes. This is the one that we already had seen, and here already with the Ytterbium Scandia printed full cell using already intermediate temperatures perovskites as oxygen electrode. So achieving much better results than the ones in the 8YZ. So this is a never-ending story, let's say, because of course we can put any complexity we can think, and this comes to my comment at the beginning, that we are coupling this with simulation because, well, we can put honeycomb, we can put corrugation, we can put squares, we can do like an hexagonal cell, we can make like a toroidal snake cell. But if you allow me here a small joke, sometimes to putting more complexity doesn't mean that you are improving the final result. So we recap a bit what we were doing with putting this complexity on our cells, and we found that one of the best solutions, or one of the best options that we were studying, was the corrugation feature of our electrolyte. So here you have a comparison, the cross-section comparing a button cell on a flat standard printed but standard flat electrolyte through to the corrugated, where we have an increase in the area of 60%. Of course, and if you are familiar with this technology, you know that if we are increasing the area, the active area by 60%, we will have an increase on the performance, on the power density, on the injected current of 60%. And this is what we prove. We prove it in 8YZ button cells. We have exactly the same increase on the performance that we have in the area, which, I mean, it's not a surprise, but it should be proof. And here it's proof, and then you would say, well, but which is the advantage? Because what you are gaining by the increase on the area, by the corrugation, you are losing on the volume. And this here it comes the idea and the different what is different from this approach and this proposal. Okay, we first characterize, as I was saying before, that everything looks like it looks on the conventional technology, even for the flat, for the corrugated technology. Here you have some details of the cross section by SEM, where we can see the precision of this printing. So when you have it in the hands, you cannot see these steps because they are very, very small. It's 25 microns of resolution in the 3 direction of the printing. So we have a very good finishing of these structures, and we can generate any corrugation that we design. Okay, and the advantage comes here because from the button cell, we pass to a larger area cells, and then at the end, we end up with this design that it's not just adding this corrugation for increasing the area, that this is one of the advantages, but also adding this corrugation for taking some of the skills, some of the things that are used on are used to put on the interconnect of this technology. So usually the interconnect piece, as we were saying at the beginning, it's a quite complex piece that has to distribute the gas through the cell, requires the inlet and outlet channels of the fuel and of the gases, and also it's used by generating this sealant that you need for the 2 chambers, the fuel electrode chamber and the oxygen chamber. Here we embed everything on the active part of this technology, on the ceramic part through the 3D printing, as you can see here. And then we have in the ceramic part the gas distribution, the points of the current collection because of the corrugation, and also the sealing frame and the inlet and outlet channels. So with this, we can simplify a lot the interconnect. So we reduce a lot the volume and the weight of the technology, and also the complexity of the manufacturing on the metal part. So with this, our single repeating unit, that is the unit of repetition that you need for generating this stack, it's reduced quite a lot. This is the conventional technology where you have the machined interconnects and the flat cell. And here we have the corrugated cell with the flat interconnects, the simple 200 microns flat Crawford interconnects. With this, we have an ultra compact technology with an improved thermomechanical resistance, and it allows us to seal the technology on this frame that can resist high pressures. So we can use, instead of the standard glass sealing, we can use compressive sealings. And this is related with this flexible dismantling, because this compressive sealant is not attached to the cell, it's just sealing by compression. So at any moment that we want to remove or replace a cell of our stack, we can just remove this pressure, of course, cool down the stack, remove this pressure, remove the damaged cell, for instance, and put another cell. So we have these advantages. This thermomechanical improvement also allows us to use pressure on the stack, allows us also to heat up the stack quicker, and the more important thing is to increase the gravimetric and the volumetric power density of the stacks, achieving, following our calculations, our goal is to achieve 2 kilowatts per liter of stack and 1 kilowatt per kilo of stack, which allows then, if we add it to the thermomechanical stability, to use this solid oxide cells technology, solid oxide fuels technology, for portable applications, aviation, marine, heavy transport. Here we have a table, very conceptual, of which are the advantages of this new technology. We call it Oxide 3D Sock because this Oxide is the name of a new spin-off that we are launching with this technology for fuel cells applications, where we can increase the power density, we can increase the mechanical robustness, we keep the advantages of the solid oxide fuel cell technology in the fuel's flexibility and fueling time compared with batteries, okay, but we increase also the starting up time, which is one of the main drawbacks of this technology. So let's say tackling all these advantages that we had in the standard solid oxide fuel cell technology. So once this idea and this concept was proved, and then we start producing cells, then we have already 45 square centimeter in projected area that with the corrugation you have to multiply by 60%, so 75 square centimeters of active area of our cells that we can functionalize with the state-of-the-art materials. Here you have the cross section, and we have this. This is the microstructure of the conventional YZ electrolyte and the interfaces between the electrodes. With it, we start with single cells. Here you have the results of already a substack test. We join 3 single repeating units of these very simple interconnects and 3 of these solid oxide corrugated membranes, and we achieve in fuel cell mode at 900 degrees already almost 28 watts per substack, and in electrolysis mode we achieve the 83 watts of power of this electrolyzer, injecting already 20 amps to each cell. Okay, we keep on scaling up this technology, and our last achievement has been already, and it has been published in the Journal of Power Sources, the testing of already 18 single repeating units stack based on 3 YZ and achieving this 330 watts at 850 degrees, which is a very nice result considering that we are using 3 YZ as electrolyte and 250 microns of thickness. As I was showing at the beginning, now we are putting efforts on reducing this thickness, and we are ready for reducing it around 100 microns per cell, and changing the material from the 3 YZ to the 8 YZ, which could multiply this power density of the stack by 3, by 4, by 5, depending on the final material and on the final thickness that we can achieve. So for producing that and for scaling up this, although we have industrial machines, we have created a pilot line in our facilities called Mercelab, Manufacturing of Energy Ceramic Devices, where we have the complete process. We start by the slurry by the preparation of the slurry. Sorry, we can prepare these photocurable slurries with any of the materials that I commented. Then we have all the steps on the additive manufacturing. I will show you then the machine we're using. Sorry. Then an industrial furnace for the binding and sintering process. All the processing for functionalization by spray or by inkjet printing of the electrodes. Then the machining of the electrolytes by water jet, the machining of the sealants by water jet, and then the stack assembly and the validation up to 5 kilowatts per stack. Here are the pictures of this new facility. The standard machines, each one laser with a 300 by 300 by 200 millimeters of printing volume. Here we multiplied the lasers by 6, so it's a 6 laser machine with 4 platforms of 300 by 300 by 200 millimeters that can operate 24/7. So we can generate this technology at megawatt scale per year. And we have also industrial furnace for curing hundreds of cells at each batch, okay? And well, here you have the picture of the screen printing for the different coatings that we need in the interconnect, and the other two machines of a single laser and a single platform. This has been done in collaboration with H2B2, that it's a Spanish company dedicated to PEM electrolysis that are diversifying their production also to the solid oxide electrolysis, and we generate this oxide as a spin-off of our institute for exploiting the fuel cell application. And well, this up to here, the scaling up of this planar cell, but I wanted also to show you other approaches that we are doing in the additive manufacturing of the solid oxide cells technology. And here I show you also some advances on a monolithic solid oxide cell with embedded functionalities. This is like a Archimedes spiral. It's a double spiral that is crossing. So we have, it's like a parking ramp, I like to say. No, we have a first ramp that it's the air chamber, and the floor of this ramp, it's the electrolyte, and the other chamber, it's the fuel electrode. We have a monolithic, we don't need sealants, and we can print this, I would say, very nice monolithic device where we can increase or reduce the pitch between these chambers and increase this gravimetrical power density that we were putting in this corrugated technology up to 1 kilowatt per kilo. Here we can go even farther to this, to 2 kilowatts per kilo of technology. Okay, here are some details of the cross section, because we can also corrugate these membranes, or we can do it planar. And here you have what is the initial design and what we achieve at the end once it's already printed. This one are in green. Here, this one is already sintered. And other approaches that we are following, it's also to print graded porosity structures. We can print porous, dense porous structures for the later infiltration, impregnation with the active phases to generate our devices. Here you have one of the cross section of a 3YZ porous dense porous structure that we later functionalize with LSM. And we perform this reversible characterization. Here you have the SOFC mode at the right side, the SOEC mode at the left side, and we achieve quite reasonable current densities with this porous dense porous approach. And we are now working on the microscale features for interface engineering of our electrolytes. What we are doing is to put pilars and modeling if these pilars can give us two different advantages. One is in the anchoring our electrodes on the electrolyte's surface, and the other is to generate some specific points of reaction on the surface of our electrolytes. These are works of the PhD students of the group that are still ongoing. Another already finished work has been the hybridization of this stereolithography technology for printing the electrolytes with the use of robocasting or the direct ink writing to perform the whole cell in a single printing step. Here you see the part of the printing of the electrolyte by SLA, and then we have 4 different robocasting needles to print fuel electrode, oxygen electrode, interconnect, and also the sacrificial material that we put on the parts that we need to have, the channels, the tracks, etc., etc. This has been hard work for a PhD student that already finished, and here you have the scheme of how it's the processing. First we print the electrolyte, then we blow the uncured paste. By robocasting we print the different electrodes, and here the critical part has been the co-sintering of these different materials with different thermal expansion coefficients, dense porous ceramics with different expansion coefficients, and how to find the conditions to make a co-sintering of everything. But as you can see here, she succeeded. Here we have some of the button cells fully printed by hybridizing, robocasting, and stereolithography technologies, and here the IV curve of this Buton full cell achieving this 250 megawatts per square centimeter. And with this, I just want to recap a bit my talk and the main concepts. First of all, and I think that has been clear also in previous talks, the importance of this hydrogen strategy in Europe and the role that will play the solid oxide technology as the most efficient one. That, of course, has to face the challenge of the high temperature in terms of material resistance, etc., but it's a very promising technology that it's already at megawatt scale, and we have already selected the good materials and the good architectures. The capabilities of the additive manufacturing also for functional ceramic materials, flexible in geometries, flexible in materials, and putting some advantages on the final devices. Here I was speaking about solid oxide cells, but it's the same for catalytic reactors, for batteries, for many other applications. And also the capacity of this additive manufacturing and our own capacity for scaling up the technology from an idea on 2016 on a Buton cell to already pre-industrial manufacturing plan at megawatt scale and testing already at stack level. And that's all from my side. I hope that you find it interesting. And if you have any question now or later, here is my contact. I didn't put my picture because you can see it here with the camera. This is the team. This is the people that makes this real thing. And we are in Barcelona, very close to the sea. And if you want to join our team, just contact me. Thanks for your attention. And if you have any question, I'll be glad to answer.
Thank you very much, Mark. We still do not have questions for you. So for the moment, let's go on. And we have recovered Annette. Annette, can you?
Yeah,
yes.
Can you hear
Yes,
me?
finally. Yes.
Sorry for the technical issues.
Right.
Can you see my presentation?
Yes, we can. Yes, try to change the slide just to be sure that everything's working right. Yes, thank you very much.
Okay, good. Then I may start?
Yes, sure.
Okay, good. Thank you very much for the invitation to this very interesting webinar. I'm coming from the Fritz Haber Institute of the Max Planck Society in Berlin. And in our group, we are dealing with thermal catalysis in reactions which are related to energy transformation and storage. And in our work, we synthesize oxides mainly, and these oxides work as host structures and precursors of active phases. So we, for example, deal with ammonia decomposition or CO2 activation. And in this case, we start, for example, also from perovskite and have such exsolution strategies like we have seen in the in one of the talks today already. But today I would like to talk about the properties of perovskites in oxidation reactions, and in these reactions the perovskite works as the materials as it is, as an oxide. At the beginning, I would like to emphasize that catalysis is a multi-dimensional phenomenon. So our active site is regarding the size in the order of magnitude of an angstrom, and the elementary reaction are very fast in the order of the magnitude of femtoseconds, but it takes reacting molecule sometimes hours or minutes to diffuse from the to enter the reactor and to fuse to these active sites through the pore structure of the catalyst. And there's another issue in catalysis, that is that the reactions that are important for energy conversion and the synthesis of chemical products with high selectivity are usually very complex. And we generally observe that the catalyst is changing under the working conditions. We have in thermal catalysis a term for this. This is formation. So sometimes you can even start with a completely inactive material, and by treatment in the reaction feed, you can activate this material. And therefore, the synthesis strategies must consider also these changes and must not taking only into account the inorganic synthesis of a solid catalyst, but also the formation in presence of the reacting gases. And I would like to show you an example for the application of perovskites in thermal catalysis in the field of selective oxidation. Here in our group, we were dealing with the activation of alkane molecules, which you can find in natural gas or crude oil, directly with oxygen to form valuable products which you can use, like olefins or oxygenates, which you can use for polymerization. There are only a few examples of such a process in the chemical industry. For example, the selective oxidation of butane to malic anhydride. This is a commercialized process. But most of the other reactions, they are not applied because they have a too low resource efficiency, mainly due to insufficient selectivity to the desired product. The problem in selective oxidation is that you easily can burn the product completely to CO2, but you don't want. And there have been concepts proposed in the literature based on empirical work, but there is a little fundamental understanding how one can improve the selectivity. And therefore we devoted our work for some time to the synthesis and investigation of these oxidation catalysts. And since the material are normally composed of many elements, we try to make phase pure materials, at least to reduce a little bit the complexity. So our aim is to minimize the materials complexity while we optimize the functionality. So we try to investigate model systems, but the model systems should be not too simple so that they show the full functionality, as work show good properties as a catalyst. And we apply operando studies. That means spectroscopic investigations while the catalyst is working. Here's an example of such a selective oxidation reaction. Also if you oxidize, for example, propane, you can undergo numerous reactions. And depending on what products you would like to synthesize, for example, acrylic acid or propylene, you need to stop the reaction at a certain point. For example, if you want to make propylene from propane, you need to prevent that propylene is further converted to the other undesired product, finally to CO2 and CO. And therefore, the control of selectivity is a very important task in thermal catalysis. I have now selected our work on perovskites in these types of reactions, selective oxidation. The perovskites, they show a compositional and a structural variety, a very nice one. So you can vary the composition in the broad range. But so far, these materials have been mainly applied in the substitution of noble metals in combustion catalysis, combustion of alkanes or volatile organic compounds, or in CO oxidation. We wanted to investigate these materials in selective oxidation of alkanes, specifically propane, And we ask ourselves how we can make these normally unselective materials selective in this reaction. Normally, these perovskites combust the propane totally to CO2. And we want to stop, for example, at propylene. So we synthesized a whole matrix. So we varied the A element and the B element over a broad range, but not all syntheses were successful. So only the green materials we achieved, but not all are really phase pure. So in some cases, we also formed some binary oxide as a side product. And in some cases, the materials are metastable under normal conditions or not stable at all under normal conditions, or require, for example, very high pressure of oxygen for their formation, or they decompose under reaction conditions. So that are the white fields here, which we are not able to investigate in our study. And how we synthesize these perovskites, we applied a very simple technique. This is solution combustion synthesis. Is very easy. You mix your metal salt precursors with some fuel. We use glycine, and then you form a gel, such a foam, and then you heat this and initiate the self-combustion. And after that, we usually calcined all our synthesis products at the same temperature somehow to have a similar starting point regarding the oxygen defects in these materials. And in some cases, we directly obtained a phase pure perovskite. But in some cases, we had some incomplete conversion of the perovskite phase or presence of Bay phases, which required a washing step. And this washed materials was again then calcined at 800 degrees in air. And this we normally don't need to do by applying flame spray synthesis. This is a very elegant technique where you can synthesize nano-sized perovskites. You have a lot of parameters that you can vary, like the flow rate, the chemical composition of your metal salts precursors, additives, solvent, and by that you can vary the flame temperature. You feed the mixture here into a flame and form in a gas phase reaction your solid. And by varying these parameters, you can control the phase composition of your product, and you can also control the particle size. And therefore, we optimize the synthesis for each perovskite, and so in this way, we came to very reproducible synthesis of very small size primary particles in which the elements are very homogeneously distributed, like in this lanthanum cobalt oxide. And if we apply now these materials in the selective oxidation of propane, in this case, our target product was propylene, which you can use for polymerization. We try to prevent the total combustion to CO2. And here you see the rate of propane consumption as a function of the reaction temperature. And then you see that normally it is assumed that manganese is the redox active element in this comparison. This manganese plays an important role, but we found also that the A atom plays an important role, and that, for example, in this comparison here, we have only compared manganese containing perovskites. The samarium is much more active than the lanthanum. But generally, if we synthesize, if we perform the reaction just in a mixture of propane and oxygen, the selectivity to our desired product propylene is very low, irrespective if we start from samarium or from lanthanum. Samarium are the circles and the lanthanum are the squares here in dry feed, these red curves. So we form only 20% propylene and 80% of our reduction product is the undesired CO2. But if we add steam to this feed, we can substantially increase the selectivity. We form 50% propylene, which is quite good for these kind of selective oxidation. We can make with steam in the feed our unselective perovskite quite selective. And we were, of course, interested about how this is going, what does the water do? And therefore, we wanted to investigate the surface of the catalyst where this happens. So if you look with electron microscopy on these materials which are phase pure, so here we have here 3 materials. The lanthanum manganese oxide we also prepared by hydrothermal synthesis, but I would like to focus on the combustion synthesis material, lanthanum manganese oxide and samarium manganese oxide. The 2 materials have different surface areas. The lanthanum has a higher surface area and the more active samarium manganese oxide a lower surface area. And the structure is also different. We have rhombohedral structure and orthorhombic structure. But both of the materials are phase pure according to XRD. But if you have a closer look with electron microscopy, you see that these materials have surface defects. So you find very different surface terminations. In some cases, you find manganese enrichment here or here, but you find also samarium or lanthanum enriched at certain positions. So you have a very irregular surface termination despite the phase purity of the material. And you can study this also with eels. So if you make, for example, for the samarium manganese oxide, a line scan from the surface to the bulk, you see that at the surface, this is this red spectrum, you have a higher contribution of manganese 2+ compared to manganese 3+. So you find a reduction of a formal reduction of this perovskite on the surface. So you have more oxygen defects here at the surface. And also manganese 2+ is enriched on the surface. And manganese 2+ can be on samarium 3+ positions or on ill-defined positions in this case. This was also confirmed by Raman spectroscopy. Here you see Raman spectra of this material, of the samarium manganese oxide, recorded with different excitation energies, also with different lasers. And if we use a UV laser, we have a higher contribution of the surface to the spectrum. And here we observe an additional peak, which is not present with this red laser here, which we tentatively assign to surface manganese oxide. So we have really an ill-defined surface structure. And this we can also confirm with adsorption studies. In thermal catalysis, we do a lot of investigations with chemisorption or adsorption to probe the surface, because this technique probes really the outer surface layer of our solid. And the best way is if we take for the adsorption our reacting molecule, the intermediate or the product. And one technique to do this is the microcalorimetry. In this technique, we put our material into a cell, evacuate this cell, and then we dose very small amounts of our molecule that we want to adsorb. And then with increasing doses, we increase the pressure. And at the same time, we measure the heat flow, and from that we calculate the heat of adsorption. And then we get such curves, the heat of adsorption as a function of the coverage or the amount of our molecule adsorbed on the surface. And we see that at a low, if you dose the first molecule, we see a high heat, and then in this case, heat goes down, and at some point it drops to the heat of liquefaction, and that means here we have reached the monolayer. So we can also calculate the monolayer capacity here, or read out the monolayer capacity. And if we differentiate this curve, we get a kind of histogram, how many sites we have with the different heat of adsorption. And the heat of adsorption tells us something about the interaction of our molecule with the surface. And if we now, for example, adsorb our reactant propane or our product propylene, we see and generate such histograms, we see that our surface is in agreement with the electron microscopy very inhomogeneous. We have different adsorption sites, weak adsorption sites, stronger adsorption sites, and in particular for our product propylene, we have weak adsorption sites which are good. If from the propane, the propylene is formed, it can then desorb if it is located at such adsorption sites. But if it is located at these adsorption sites with a high heat of adsorption, a strong interaction, it may remain on the surface and be further oxidized to CO2. And our aim should be somehow to identify the nature of these sites and to, by synthetic means, avoid the formation of these sites. Okay, but this is a measurement that we do in thermodynamic equilibrium. So we adsorb only the propane or the propylene and not our reaction partner oxygen. But we are also interested in what is happening if under reaction conditions, why propane is reacting with propylene. And to analyze the surface in this case, we use synchrotron-based X-ray photoelectron spectroscopy. And this is a very good technique because we have here a very high sensitivity, much higher than in the lab XPS, and we can probe really the surface because we can, we have compared to a lab source, we have much lower, we can vary the photon energy continuously, and we can have a much lower inelastic mean free path, means information depths compared to a lab-based source, lab XPS source. And we can also do a depth profiling, and more important, since we have such a high and generate such a high amount of electrons in this experiment, we can also do measurements in presence of the reactants, so ambient pressure XPS. And so we did also with these perovskites and investigated the surface of the perovskite in presence of propane and oxygen. And normally, if we look at an ideal structure of a perovskite, our surface looks like this. We see on the surface only the lattice oxygen. But in reality, we see many different oxygen species, and the oxygen species are the active species in our propane oxidation. They abstract the protons from the propane molecule to form propylene. And therefore, we are particularly interested in the oxygen species at the surface. And if we, for example, look at the O1S spectra, we see, and here this is only in oxygen, the pretreatment of this catalyst, while we go in oxygen from room temperature to our reaction temperature, 270 degrees Celsius, we see that the profile of this O1S signal is changing very much. So we change our oxygen species, and to find out what these oxygen species are, we did a lot of fitting. I come to this in a moment. We not only investigate the oxygen species, we also investigate the concentration of the A and B sites on the surface. And we see, if we compare with the bulk analysis by XRF, that we have for the samarium perovskite slight enrichment of this manganese on the surface compared to the bulk, which is not the case so for the lanthanum. And if we follow the different reaction conditions, so we go from room temperature in helium to reaction temperature, then we add the reaction feed, propane plus oxygen, then we add steam, we don't see much changes in the composition at the surface. But we see by doing this that the oxidation state of manganese is changing. Here, this is a determination of the manganese oxidation state based on XPS. We can also look on this with X-ray absorption spectroscopy. And here we observe that in the wet feed, where our catalyst becomes more selective, we observe a further reduction of our surface. We observe if a small difference between dry and wet feed, and if we make a different spectrum, we see that the contribution of manganese 2+ is increasing. So, and now coming back to the oxygen species, here is again this increase in selectivity from dry feed to wet feed shown. And we see that if we look at the signal, O1S signal, it is different in dry and wet feed. And we fitted these spectra and into many components by doing a lot of reference experiments, so, which I do not explain here. But they are normally composed of the classical regular lattice oxygen, then oxygen which is somehow close to a defect. Then we have the adsorbed oxygen species on the surface, oxygen species belonging to some hydrocarbons, also some products, which are oxygenated, the carbonates and OH groups and water on the surface. And if we follow the concentration of these oxygen species in this operando experiment, we see that if we maybe we concentrate here only on this red area here, we are in a dry feed. We have a mixture of propane and oxygen. And then if we switch on the steam, where our catalyst becomes more selective, this we see also in a mass spectrometer. Here more propylene is formed. This is a propylene signal, and this goes up if we switch on the water. Then we observe that in particular the OH groups are increasing, which we can understand. But also we have more electrophilic oxygen on the surface, which we found very much surprising. But really an explanation of our higher selectivity we could not find from this experiment. We only saw that we have an adaptation of our surface to the reaction conditions. And if it becomes more selective, it changes also. And we also observed, I go back to this, very slow changes in the oxidation state. For example, here you see the same basically conditions like before, and you see a different manganese oxidation state. And that means there are some solid state processes ongoing in addition to maybe fast surface processes, which also may change the reactivity of our perovskite. In another study, we found also that the bulk of the perovskite is changing periodically with our reaction conditions. In this case, we started from manganese, A manganese perovskite, and we substituted partially the manganese by copper. And we synthesized the whole series. Here is the copper content shown, also with a series with increasing copper content. And all materials are still phase pure. And as A, we have in this case lanthanum and praseodymium. And we analyzed the structure of all these materials in this series very carefully by Rietveld refinement, also by XRD, classical techniques, and we found that the substitution of manganese by copper gives very complex correlation. We never found any linear correlation of the lattice parameter, for example, with the copper content, and other structural parameters were also not following linear correlations. Interestingly, we found that the cell volume changes reversibly if we reduce or oxidize our material. And this is something what we are doing if we are performing such a selective oxidation reaction. It's a redox reaction. And we studied this here just by reducing in hydrogen and oxidizing in oxygen, and we observed that in the reduced state the cell volume is bigger, and in the oxidized state the cell volume is lower, and this is a little bit different depending on the copper content, but this is not a linear relationship between the copper content and this behavior. And we observed that, so to say, during redox reaction our perovskite is breathing like in and out oxygen and changing its volume. If you look at the catalytic properties in the propane oxidation, we couldn't find any parameter of these structural surface parameter, whatever parameter, any physical property of our catalyst in the whole series that somehow correlates with the selectivity to propylene in our reaction. You only observed that the amount of exchangeable oxygen we determined from these experiments here, from this breathing in and out oxygen, is correlating with the activity, but interestingly in a different way we expected. So if we have a high amount exchangeable oxygen, these materials are more selective compared to a low amount. This is something we observe in many complex reactions, like which have such a complexity like the selective oxidation. Therefore, we go also another way. We try to apply machine learning to understand which physical parameter of our catalyst is the most important one. And this we have not done yet in this case for perovskites, not for the selective oxidation of alkane, but just for CO oxidation. So we took our nice matrix here of the different perovskites, and the dark green ones that we have prepared and we have tested in CO oxidation. And what we determined is here the temperature at what 10% CO is converted into CO2. And the red, in this dark green materials and the catalytic testing and all the characterization of these dark materials, we put into a machine learning algorithm, and the red areas were predicted from this algorithm. And then we synthesize the materials, and we can see that they fit very well, but I need to explain what this algorithm is doing. The algorithm is taking the catalytic performance, in this case, the conversion at 10%, and this is the target value, and is trying to fit physical properties we measure for this catalyst with these data. If we do this as a human by hand, so we, for example, try to correlate the measured temperature with the surface concentration of our B cation. we do not see any correlation. Then we have correlated by hand, so to say, the activity with the ionization energy of B, also no correlation. And our machine learning algorithm gives us this complicated formula, which gives this fit. And from this formula, we learn somehow if we have a high ionization energy of B, this is good for, this is, bad, because we need to have a low T10, a low temperature for 10% conversion. And it is good if we have a big change in this. This is the normalized cell volume, a big cell volume, and we have high Pauling electronegativity of A and B. And using such a formula, we could predict new perovskites, and we were even able to predict perovskites which are very complex composed and have nothing to do with our training set. With this, I come to my conclusions and take-home messages. I would like to demonstrate, for the example of thermal catalysis on perovskites, that these materials are interesting in thermal catalysis due to their compositional and structural variety. However, it's very difficult to control their functionality in a catalytic reaction via synthesis, because we have very complex correlations between the composition, the bulk structure, and the surface chemistry. And this changes also under reaction condition. And to help here, we can use artificial intelligence. If we provide reactivity data and characterization of the material in a very consistent data set, and then this technique can help us to predict new compositions that we then try to synthesize. With this, I come to my end. I thank here the sponsors and collaboration partners, and you for your attention.
All right. Thank you, Annette. So if there are no questions also for Annette, let's just wait 1 minute to check. So, okay, while we wait this minute, I want to remind to all the audience here that we are organizing a summer school that will take place in Italy. So the registrations are open and you can register already. It will be from the 7th of July to the 10th of July and will be held in Rovereto, Italy. So we are still organizing the agenda for it, but you can still look it up in our website, on Knowskite-X website. So no questions for the moment. So I thank all the speakers that joined us today, and also you as audience for your participation. And that's it. Thank you very much. Keep following Knowskite-X on the website and social media to know about other similar events in the future. Thank you very much. Goodbye. Have a good day.
Goodbye.